All right. Hello, everybody. My name is James Braza. I work at a company called FutureHouse. We are a focused research organization based in San Francisco, philanthropically funded, and trying to build an AI scientist. If you've been to FutureHouse before, raise your hand. I recognize some of you guys for sure. And if you work at FutureHouse, raise your hand. All right. The past year, I guess, we've been building several algorithms. And today I'm going to talk about them. These are algorithms that build on themselves in a concept from the AI ML community called recursive self-improvement. And I'm calling it the Edge of Tomorrow algorithm. If you've seen the movie Edge of Tomorrow, it's when Tom Cruise, who's playing this guy, William Cage, he gets trapped in a time loop. And he relives the same day over and over until he can save Earth from these aliens invading. There's a couple other movies where the same thing happens. Palm Springs, if anyone's seen it. Groundhog Day, this character Phil gets trapped by Punxsutawney Phil. And then Happy Death Day, which is when this woman Tree has to escape this masked killer. I'm a member of the SF Systems group, recently joined the SF Systems Club. I like systems thinking, and I think when you're doing your work in the MLAI community, a lot of it is systems thinking. And so the algorithms I'll talk about today are based in systems design thinking. The first class I would like to talk about is data flywheels. So data flywheels are algorithms where you start the day with better data every day. So the first one, simple one, is called expert iteration. Expert iteration, you start out with your initial policy. Your policy is your model. You can think of it as a llama 8B. The goal is we'll repeatedly supervise, fine-tune this model over and over on completions from the previous model, and those completions are getting better over time, and through more fine-tuning, your model gets better. So we'll enter a loop here with your initial policy. We start out with a batch of rollouts, which is basically prompting your model a batch B times, where each prompt is a different prompt, and you get a bunch of completions. Each completion has a reward assigned to it, and a higher reward is assumed better. So if you get a reward of 1, that's usually correct. 0 or -1 is incorrect. So one of the parts of expert iteration is you do this next step called rejection sampling. Rejection sampling is when you remove the wrong or incorrect or flawed outputs. And so here we can use reward. We'll just filter for not 0 and not negative rewards. Given that data set, we'll now supervise, fine-tune our model, and we get a new model, an updated policy. And we can use this updated policy to re-enter the loop and do another set of rollouts, and we'll repeat this loop n times. And at the end of it, we arrive at our final model. And this algorithm resembles the movie Edge of Tomorrow because Tom Cruise wakes up and he starts his day and he ends up getting killed by the aliens. He has better data and he restarts. And at FutureHouse, we used expert iteration last year in this aviary paper where we used it to fine-tune repeatedly llama 3.18b. Iteration over iteration, here are the green lines here. Eventually it surpassed the frontier models of the day, GPT-4o, Claude 3.5 Sonnet. This is the general theme of recursive self-improvement, where you are piping outputs of the model back into itself. So the next one I would like to talk about is one from earlier this year. FutureHouse trained a chemistry reasoning model, and the algorithm here is called expert iteration reinforcement learning. And so it builds on previous techniques using reinforcement learning. We start out with our initial policy. In this case, it was an instruct model from Mistral 24B. You in your own data for the start of this one. We took our training data, prompted it to DeepSeek R1. DeepSeek R1 sucked at our task. Our task was novel chemistry tasks, and it got, I think, less than 10% accuracy, but that was all right. We just needed to start the loop. We'll use that, and we begin by supervised fine-tuning on, we supervise fine-tune our Mistral on that data, and we get a fine-tuned Mistral. From there, we'll enter reinforcement learning with verifiable rewards, RLVR. RLVR is a big buzzword, but basically the difference with supervised fine-tuning is it's one time offline, you blow through a data set. Here, every batch, our model is being improved in place for the next batch. And so we run a batch of B rollouts, and then there we run another batch of B rollouts, and each time the model is getting better, and we arrive at our updated policy. So this updated policy has gone through supervised fine-tuning and then reinforcement learning. So it's been updated twice. Now this is an expert iteration variant, so let's do our rejection sampling, filter out the incorrect. So in this case, we're using the RL portion to create this rejection sample data. Now we have maybe done many batches, so there's other things you can do. We filtered out times when the model used other languages. Sometimes it would speak other languages. We would go with the latest one, maybe hoping that's the smartest later on. And then you complete this in a loop. And we do this loop in times, and we arrive at, once again, our final policy. So in this loop, the difference with the previous one is it's even more like Edge of Tomorrow because we're starting with an initial policy every single time. And the previous expert iteration algorithm, we started fine-tuning the same model, but our starting point was more fine-tuned than the previous one. This one, it's actually the same starting point every time. The difference here is that our initial data is getting better. So this is actually pretty cool because that initial data is an external asset that you can then reuse, it becomes valuable, and you can apply it to any model. We use EIRL in our Ether0 paper. Ether0 is our chemical reasoning model. And the reason we use DeepSeek R1 was to elicit reasoning in our non-reasoning starting model, the 24B instruct. So shown here, this first box, this is the fine-tuning, supervised fine-tuning. And then we did, we had all these chemistry tasks. We did 9 of them. You can see we start out low, get high, long story short. And then we did a second loop where all of the fine-tuning happens at everything all at once. And we were able to take 9 different tasks and basically through EIRL multitask train our chemistry reasoning model to be the best chemistry reasoning model in the world right now. And that may be controversial, but it's true. In my mind, it's true. Actually before I move on, I guess the general theme here we've talked about is improving our starting point, but in these Edge of Tomorrow algorithms, there's other ways. Because we're using systems thinking, we'll think of different ways. So perhaps instead of starting further ahead, what we'll do now is better pass our model data so that it can move much further in the same unit of time. We use this advantage-based curriculum learning technique. So curriculum learning is a big buzzword for trying to give your model easier problems to medium problems to hard problems. So as the model trains, the problems get harder. Here what we did is our chemistry problems were totally new problems. We had no general heuristic for defining their difficulty. So we let our model define the difficulty. And so what we would do is in our loops we've been talking about, in the previous loop, which you basically have for free because you already ran it, when we prompted the model, now we were doing GRPO. For those who, okay, GRPO is beyond the scope of this talk, but it stands for Group Relative Policy Optimization. What is a group? A group is basically concurrently prompting your model G times, where G is your group size. And the different items in the group, you can compare them and try to learn from the better performing members. Now, in machine learning, the term for better performing relative to others, and the relative is where group relative comes from, is called advantage. And so if no completion has an advantage above 0, if they're all 0, we can declare that it was too easy or it was too hard. Basically, the model didn't get any traction, we can't learn from it. But if that problem had a mixed advantage, meaning there was a problem that performed relatively better than the others, we can learn from it, and we declare it as non-trivial. It's medium difficulty. And so on this previous iteration, we built this buffer. So in this next iteration, we take our previous buffer and our training data, and we feed it some fraction of the time problems from your known learnable problems. So basically, what does this mean? This means in the previous iteration, we memorized what problems we could learn from, and then we just refed those problems in the next iteration, and it's totally for free. And it's actually really well. So this blue line here is without this technique. And we can see that about 30% of the time, it is, throughout the whole training, 30% of the time, it's only learning 30% of the problems. Those are the non-trivial ones with the mixed advantage. But when we use our technique, the curriculum learning, this advantage-based curriculum learning, we bump up to 50% throughout the whole training. So 20% of the time more, the whole training, literally for free. And how does it actually work in practice? This other plot is the evaluation rewards. We see the curriculum learning, pink line is above, but what it actually means in practice, let's look at the ending point. The final reward is 0.55. We attain that in half the time. So another advantage of this algorithm is it's just totally for free, and you get twice as good. So that's what I mean by these recursive self-improvement algorithms. They feed in, and then you can apply them for free. So if you're Tom Cruise and you want to beat the aliens, now you can run twice as fast or something. I don't know what the analogy there is anyways. Overall, these are the three algorithms. Expert iteration, that was completed previously in FutureHouse. We created the second two, expert iteration reinforcement learning, and the advantage-based curriculum learning. Shout out to Sid, he's the first author on both of the papers referenced, and thank you for attending. Questions?
Versus feeding it. I was curious why you did the rejection sample data technique to filter out wrong prompts versus feed that back in as hey, you got this wrong. So to not use that information that the model was getting something wrong and just totally filter it out and then just redo it.
Yeah, the question is there could have been learnable signal in the incorrect ones. Maybe we can learn from the wrong ones.
Yeah.
Yeah, I think that's valid. I think that's totally valid.
Good. Cool. I was just wondering if there was a reason that it was polluting it or something, or if it's just maybe down the line you could try it including that signal. Yeah.
I think in our use case the wrong ones would be in the EI algorithm that I'm talking about, our task was an agentic task. It involved a lot of tool use. And so I think the model was just misusing tools. And if you only fine tune on correct tool use, it would help. But that's actually a great question, yeah.
Makes sense.
On your advantage-based curriculum learning model, are there specific tasks that it does better on than other tasks? Are you doing, yeah.
Yeah, the question is the advantage-based curriculum learning, does it apply better to some tasks than other tasks? And the way it works is you start a problem, you find out if it was too hard or too easy, or if it was medium difficulty. And in that sense, it can apply to maybe any problem. If the problems have all very similar difficulty, then maybe it is less useful, yeah. If the model is finding everything learnable or finding nothing learnable, then the advantage-based curriculum buffer, you need to get it hot, you need to get it warmed up, and if it's not hot and it's not able to get hot, then yeah, I think it wouldn't work as well. Yeah. Yeah.
I was curious. Super interesting. I was curious what kind of problems you ask it. Are they typically more Olympiad problems? Are some of them open-ended? Are some of them even problems to ask different kind of questions? Maybe some context on that would be cool.
Say the last part again?
Would there be any problems that the right answer is almost asking the right question? Is there anything like that? I was just curious in the types of problems. Yeah.
Yeah. So our tasks are at FutureHouse. We have these scientific tasks. So it's could be given half a molecule and that it needs to smell like flowers, provide the other half of the molecule. Or it's literature, question answer, sequence design. They're not incredibly open-ended. They're not like math. We actually have a team that makes these evals up. They are novel. They're made within the last year or something by basically the evals team we have. but they're not like totally open-ended. Is your question, are they like super open-ended or?
Yeah, are they super open-ended? Are they super like closed, almost just mathematical? Like, are they somewhere in between? And maybe like, even how does chemistry as a subject like affect those kind of problems versus like physics versus math versus bio?
So this like reasoning model effort is interesting in the sense that you can, when you're training your model, you can choose to look at the reasoning, or you can leave the reasoning totally unattended. And if you are actually putting the reasoning under the scope of your optimizer, the optimizer may affect the reasoning, but if you don't, the reasoning will be maybe more faithful, more natural. And the Ether 0 paper, the second algorithm, that EIRL, was a reasoning model. And I think that the problems we faced, which is reason a bunch about chemistry for free, it's your scratch pad, and then answer, that would apply to anything in the STEM domain. Now, in the paper, we did find that some tasks didn't get much advantage from reasoning, in which case those were just better suited to memorization. Sometimes it's nice to reason, sometimes you just spit out the answer. And I think that can apply maybe to different types of science problems, like maybe physics, you always want to reason, but elementary math, you need less steps. Yeah, maybe if you ask me that question again, I'd give you a different answer, but that's just my answer this time, yeah.
Oh, can I go? Yeah. So I'm using a lot of this for a different problem. I'm using at Meta, a lot of the ETHRO stuff. Have you guys experimented a lot with multi-turn RL? Because basically you can get like verification of something works or not, and then you reason it back, and like having that be something useful for it. I'm just curious because that's kind of the path I'm going down right now to solve our problems.
Yeah, that's where we're headed next to, for sure. That's definitely very interesting, where you do something, you get it wrong, you get signal, you keep going, basically, and you try again. Yeah. I think that's our next step. It's very interesting and promising. Yeah, it's science. I think that is science. So it'll be good. Yeah.
Yeah, like what sort of practical tasks do you see this like over like basically working on immediately?
Yeah, the question is like, what sort of practical tasks do these methods apply to? I think recursive self-improvement is really cool. First of all, you have a model improving itself over time. And I think there's many opportunities for recursive self-improvement. As far as practical tasks, maybe if we look at like a software engineering application, if you can train your model to be a better software engineer, you can solve a new type of problem. And then you start again, and because you can do that new type of problem, now you can solve 2 more types of problems. So in general, it's about gaining traction and hill climbing. And anytime you want to hill climb, recursive self-improvement is pretty cool. And in general, I think like if you get the opportunity to think about how can I close the loop, that's just like really fun. Yeah.
Thank you.